In this video, I discuss the Gaussian Plume model. Special emphasis is given on presenting the Gaussian Plume equation here in a way that is easy to understand. The video may be a bit long, but it is important to watch it till the end for complete understanding. We know that almost every human activity and natural process contributes to some level of air pollution. However, the impact of this pollutant on human health and the environment depends largely on how they disperse in the atmosphere. Air dispersion modeling is a powerful tool used to predict the concentration of air pollutants over time and space. It helps determine whether the particular source of pollution poses a significant risk or remain within the acceptable limits. If the ambient concentration of an air pollutant or combination of air pollutant at any location exceeds the acceptable limit, it becomes a cause for concern. Acceptable limit depends on regulations, toxicology, ecotoxicology, or simply the well-being of the local population. The most common air pollution dispersion model is Gaussian Plume model. Carl Friedrich Gauss was a brilliant German mathematician and physicist who made major contribution in many fields, including number theory, statistics, astrology, geometry. The Gaussian distribution is named in his honor. Before going to the model, we have to know what is normal distribution or Gaussian distribution. Normal distribution is a type of probability distribution that is symmetric around its mean. So this is mean, and the graph is normally distributed. The graph of a normal distribution is look like a bell-shaped curve. All three measures of center tendency, that is mean, median, and mode, are equal and located at the center of distribution. For example, this is a bell-shaped curve of human height measurement. X-axis represents height in inch and y-axis represents the relative probability of observing someone who is really short or tall or has the average height of 70 inch. The width of the curve is defined by standard deviation. If the standard deviation is 4, 95% of normal distribution falls between plus minus 2 standard deviation around the means, that is from 62 inch to 78 inch. Data near the mean are more frequent in occurrence than data far from the mean. So normal distribution are always centered on the average value. Central limit theorem states that the mean of sufficiently large samples from any population that is normally distributed, even if the population itself is not normally distributed. As we already know, mean determines the center of the distribution and standard deviation determines the width of the distribution. Just like the bell-shaped distribution curve, histogram can be used to calculate probabilities and statistics. So the equation for the normal distribution curve is fx is equal to 1 by sigma root 2 pi into e to the power minus x minus mu whole square divided by 2 sigma square, where fx is the probability density function. It represents the probability density at a specific value x, mu is the mean, sigma is the standard deviation, and E and pi are constants, and their values are 2.718 and 3.1416 respectively. The reference slide at the end of this video gives you few YouTube video links. If you have enough interest to know the mathematics of this equation or how it comes, you can visit those channels. The Gaussian Plume model is based on a formula that describes the three-dimensional concentration field generated by a point source under stationary meteorological and emission conditions. Consider a point source releasing pollutant into air at a constant rate q. The wind is blowing continuously in x direction with a speed of u, and we know that a higher wind speed disperses air pollutant more, leading to lower concentration downward. So the ratio q by u indicates how much pollutant is emitted per unit of wind speed. So I just give a name to the term q by u as pollution flask per unit wind speed. You just remember this equation, this ratio and the term. As the plume moves in the x direction, the local pollutant concentration C at any point in space follows a Gaussian or normal distribution, that is follows a bell-shaped curve about the center line. This is center line in both vertical plane here and also in the horizontal plane. So we now see first the profile shape in horizontal plane. So this is a top view of plume concentration profile. Wind is blowing in this direction, and this is y, that is horizontal distance from the plume center line along crosswinds, and this is the sigma y, horizontal dispersion coefficient or standard deviation. So the mathematical formula of profile shape of horizontal plane is like this. If you recall the normal distribution curve formula, we just replaced a x minus mu with y, because this is mu and this y is x minus mu. So this is replaced by this, and sigma is replaced by sigma y here. And for the horizon and for vertical plane, this is a top view of plume concentration profile, and z is the vertical distance and sigma z is the vertical dispersion coefficient. Then the mathematical formula of profile shape of vertical plane is like that. We just replace this y with z and sigma y with sigma z. So the parameter sigma y and sigma z depends on the distance from the source and the weather condition. So if we multiply this, we get the mathematical formula of plume concentration in 3 dimension. So this is the multiplication product of these two. So I termed is as shaping function. So you just already I give a term of the ratio q by h as pollutant flask per unit area, and this as shaping function. So assume a pollutant source is on the ground, that is h is equal to 0, and x is the distance downwind from the source, y is the distance crosswind from the source, and z is the vertical distance. So the concentration at any point is expressed as C is equal to pollutant flask per unit wind speed into shaping function, and I just replace this with q by h and the shaping function. And we can rewrite this sentence like this: e to the power is exponential like this. So this is our first equation arrived. This first equation arrived for Gaussian Plume model. But if the source is elevated, that is h not is equal to 0, the dot modification is required in the formula. So suppose a stack with height h, this is stack height, releasing pollutant into air. If the plume rise is del h, so del h is the from stack height up to the central line height, it is del h is the so the effective stack height capital H would be small h plus del h. Hence, to account for this elevation, the vertical coordinate z in the dispersion equation must be adjusted related to ground level. So the z is replaced by z minus h in this equation. This equation is we have already discussed. So in this equation we just replaced z with z minus h, because in this equation this is actually z, but here from groundwater to this point is z, so we have to deduct this effective height to get this portion from center line to the point. So the modified equation becomes like this. I put here 0 to understand that here a stack is on the ground, and now I put h, that is h is not equals to 0, and only z is replaced by z minus h whole square. So this may be called as Gaussian plume model. So here one thing, u is replaced by UH, which is the average wind speed at effective height of stack, because wind speed depends on height. So wind speed at the effective source site is given. So you can rewrite is UH as U bar also. So this equation can be considered as Gaussian Plume equation. However, the effect of ground boundary is not considered. So in practice, boundaries usually play a role in air dispersion, in particular the surface. As the plume spreads, the upper part of it continues to disperse into atmosphere, whereas the lower part hits the ground in the downwind direction. So assume there is no plume deposition on the ground and the plume reflects back into the air. So to calculate this effect of ground boundary, a imaginary mirror image source is defined. So the vertical distance to P from the center line of the imaging source would be, so this is the center line of this image source, and from here to here is, this is z, and we just add h here, so z plus h. So this equation we have derived earlier, I just written here. So what modification is required? We have to plus this equation with same but z plus h. So the revised equation is becomes, so this portion will be the common portion, so we common in out, and within bracket this portion comes plus the new the effect of ground boundary is added. So here, so this is the final Gaussian plume equation considering the boundary effect. So this is we call this is as the final equation. And now one by one I discuss about different condition or different plume source, what will be the actually the changes in the in this equation happen. So if the pollution source lie between an inversion cap, what would be the concentration? When the pollution source lies within an inversion cap or flip, two horizontal parallel boundaries defined. One is here in this picture and another is here. So two parallel two horizontal parallel boundaries defined the atmosphere mixing zone. So this is mixing zone here, and mixing zone, and the indefinite number of plume deflection can be occur, and this would lead to an indefinite series of image sources located at h plus 2jl and minus h plus 2jl, where l is the height of the inversion layer and z is the integer to to model multiple reflection or image between ground and inversion layer. In this picture, one real source and five imaginary source is described. So how what changes will happen in this equation if this plume source is within the inversion cap? So to account the multiple reflection, the Gaussian plume equation is modified in the following manner. So we keep this as it is, and in the bracket portion where we write, we just change h with h plus 2jl in both equation, but summation of uh, j is equal to minus infinity to plus infinity is given. So if in this equation, if j is equal to 0, then this portion becomes 0 and this is 0. So this equation will arrive. So if j is equal to 0, then only this portion, this equation uh, will be the will taken. That is only ground reflection is taken. But if g it is taken at -1 to +1, j is equal to, then this the particular uh, reflection image is taken into account in this equation. So this equation satisfied both ground reflection and top boundary condition using the method of image. Now, if we going to concentration of ground level concentration where z is equal to 0, if h is not equals to 0, but we have to know the ground level concentration. uh, since our concentration is going to be only the receptors, that is people or pollution, so ground level concentration of this equation is required. So this is our final equation, and if I put z is equal to 0 here and in this position, so the equation would be like this. So this is, the modification, and when this portion becomes same, so this will be the 2 exponential minus h square by 2 z sigma z square. That's why 2 and 2 is cancelled out. So this equation does not contain any 2 in the denominator part of this ratio. So if both z is equal to 0 and y is equal to 0, that is ground level concentration is at central line is measured, then the equation is modified. We take this equation and we put y is equal to 0 here, then it becomes very simple one. Only this portion is formula is used to get the concentration at ground level on center line. So if GLC as x-axis and h is equal to 0 also. So if h is equal to 0 here, so when the source, in case the emission source is at ground level, so both h is equal to 0, y is equal to 0, z equals to 0, so it becomes more simplified and this portion is used. So here I just change mu h with mu 0 because uh, so u is equal to u h is equal to u 0 because here height is 0. So this equation represents the maximum ground level concentration expected at any distance downwind from the emission source, which is at ground level. So but if we going to know the maximum GLC from an elevated source, because it was the maximum GLC for source at ground level, but if elevated source, then for an elevated source, maximum ground level center line concentration at any distance downwind from the emission would be reached when sigma z becomes h by root 2. So if I substitute sigma z by h by 2 is in this equation, then we got this, sigma z here we put this value, so it is cancelled out, and here both sigma z are multiplied, here 2 sigma z and sigma z square, so this becomes like this. You just put it here, you just multiply up and down with sigma z here and just change this sigma z with this, and this sigma z square again put the value h by h square by 2 accordingly, then we reach this equation. So here you can see that the all things actually the constant except h. So here the C concentration is inversely proportional with with the with the height, square of height. So as the stack height increases, pollutant concentration at ground level decreases quadratically. The equation clearly shows why the pollutants are emitted into the atmosphere through tall stack. So if you want to know more about maximum ground level concentration for an elevated source, you can you can just read the book Environmental Pollution Control Engineering by C.S. Rao. So what is the assumption of air dispersion modeling? Rate of emission from the source is constant. Wind speed and wind direction and constant both in time and with elevation. Pollutant is conservative, that is, it is not lost by decay, chemical reaction, or deposition. When it hits the ground, none is observed and all is reflected. The terrain is relatively flat and not covered with scrub or has few trees. So it is, what is the advantage? It is not possible to measure the air quality at every relevant location all the time. if a new source of air pollutant is planned, air dispersion models can predict the impact of the source on the air quality. When air pollution is found, dispersion models can help determine the source. When when a source creates an air pollution problem, dispersion model can determine the emission reduction required to solve the problem. Air dispersion model can be used to plan the response to emergencies such as accidental leaks. So this is our reference slide. You can visit the YouTube channel and also go through the books for better understanding. Thank you. Thank you for watching this video.